Okay. So with that, we are going to put stress aside for a minute. And I'm going to introduce the material time derivative. This is also sometimes called the total derivative or the convective. Derivative. And this is a concept that, while the equation's not hard to understand, like exactly what it was, took me a while. Took me a while to kind of really wrap my head around it, develop a good thought experiment. But I think I have. So if you'll bear with me while I show you my artistic abilities, I'm going to draw a figure, and we'll talk about it. Okay. So imagine we have a river. And on the bank of the river, there's some type of plant. And the plant discharges, it's supposed to be just clean water, but it discharges into the river. And then one day there's a failure in the plant, and all of a sudden the plant's, oh, I don't like that color. Red's a good color. All of a sudden the plant begins to discharge a plume of contaminants. And your boss tells you to go out and monitor the plume to see if the problem is getting worse. Did we fix the spill? Is it under control or not? Okay? So I can think of two ways to do this. One way would be to orient yourself on the bank and you can take a probe, stick it out in the plume and monitor it over time. Okay? And so if we do that, what you might see if you looked at the concentration of the plume over time, you might see something like this, which in this case might suggest that it's getting worse, right? Because the concentration is increasing, right? So if I'm asking you, if I'm your boss and I'm asking you, go and monitor the plume to see if it's getting worse, what I'm asking is go monitor the rate of change of the concentration over time. Is it getting worse or is it getting better? The rate of change of the concentration, the derivative, right, with respect to time of the concentration. All right. How else could I monitor the concentration?
By pictures.
No. We're going to do it with the same probe. But how else could I do it? I could orient myself in a boat, right? So in this case, I'm just standing on the bank measuring this.
Yeah, you're in one position.
But I could also put myself in a boat and put my probe in the water, right? And of course, now I'm moving with the flow, right? the flow of the river, right? So I'm moving with the flow of the river, and so a little bit later in time, I'm here. And then at a time that we'll call t equal to 0, we'll assume that my probe is superimposed with the probe on the bank. So this is t equal to 0. T equals t0, we'll say. And so this will be t0. I'll draw my other plot in a second. But, you know, sometime later, I will be over here. And sometime even after that, we'll be over here. So we'll call this T2. We'll call this T1. Right? And so if I then monitor the plume, say T0 starts here, so my T0 value should be exactly what it is on the other plot. So say here, but over time, again, this is concentration. And so just to be clear, for example, this might be T1, and by the time T2, I'm over here. So the two ways of measuring the plume has given me, again, if I'm looking at the rate of change of the concentration, it's giving me two different conclusions, right? Here on the bank, it looks like things are getting worse. But if I'm in the boat, it looks like things are getting better. Right? Concentration versus time is going down. Well, from the experiment, from the thought experiment or the drawing, you can see the reason the concentration is going down is because I moved out of the plume. You know? So let's try to rectify that. What we're going to do is we're going to draw a coordinate system. This is our inertial frame. And we'll draw a vector to the t equals 0 location. And we'll call it, what do we call it? A position vector to the t equals 0 location, or the reference location. What do we call it? What would I label that vector? Huh? Big X, right? Position vector to the reference coordinate, right? And we'll draw another vector over here. It should be clear that this is just a vector at t equals t2, but that vector follows the boat, right? And we'll call that the current position of the boat. So therefore we'll use little x. And little x is a function of time. Big X is not a function of time because it's our reference. You know, it's by definition time t equals 0. So there was a reason I wrote my C's kind of far away from the axis here, because I want to be clear. This plot, this C is a function of big X, right? Because I'm standing on the bank and I'm not moving, right? So it's a function of big X and time. This C, maybe I even need to move it out a little further, is a function of little x, which is a function of time and time. So if I compute, and I'm gonna use this symbol d, big D, dt. If I compute big D dt of c of x and time, then I simply get partial c partial t, because this is, I use the sign big D dt to imply like a total derivative, right? I'm going to take the derivative with respect to everything in there, and because x is not a function of time, doesn't change, then the derivative, the d dt of x is 0, and so then all I end up with is this. However, over here, I have d dt c of x and t, and if I take that, then what I get is by partial c partial t plus partial c partial x partial t by the chain rule, right? So another way to write that is partial c partial t plus grad c dot v, right? So this x is a position vector, the time derivative position vector we call velocity, right? And this is a gradient operator because x is a vector, right? C is a scalar in this case, so in this case the gradient of a scalar will give you a vector. You have a vector and a vector, you take the dot product, it gives you a scalar. That's a scalar. Whenever you're doing continuum mechanics and working with tensors, scalars and first and second order tensors, it's always useful to look at your terms and see if they make sense. So in other words, this is clearly just a scalar. So whatever I add to it better be a scalar or it doesn't make sense, right? So then I start to look at this term and it's like, okay, that's a vector, that's a vector. Multiply it, dot product, the two of them, I get a scalar. And then I can add a scalar to a scalar. Okay, so what this represents is the local rate of change. So that's how is the concentration changing at in any one location, just due to the natural, say, diffusion, right? If you were to freeze the boat for a second, if you were to stop the boat for a second, this is what you would measure, right? And the other thing, this is the convective rate of change. Hence why it's sometimes called the convective derivative, right? And so, in this example, we took there was a specific thing we were measuring, that's the concentration. But this derivative operation, the material time derivative operation, we can write just generically like d dt of something is equal to partial t of that thing plus the gradient of that thing times the velocity vector. So that is the rate of change that you would experience if you're moving with the flow V. And then, yeah, so this is the material time derivative. And, you know, again, our example was for a scalar quantity, the concentration, but this works for vectors too, right? So if I put a vector in here, like to take the time derivative of a vector, I get a vector. If I take the gradient of a vector, I get a tensor, and then I'm multiplying by a vector. So I get a tensor times a vector is a vector, right? I get a vector plus a vector, it makes sense.
Can I extend a bit more on the thought experiment?
What's that?
What if you're on the boat moving, but what if the river is flowing with the same speed? In another scenario, what if the river is flowing with a different speed? So how's that equation gonna change?
Well, the speed is here, right? This is the velocity of the flow. It's the velocity of the river. So if you measured it at one velocity, you can imagine, okay, in one example you're going to float through just with the velocity of the flow, and in another example you're going to go through with a motorboat,
Yes.
right? So now the velocity would be the velocity that you're traveling through the river in the motorboat, right?
So, but what if the flow is steady in the river? For the river,
Flow is steady.
for the river, not the boat.
I guess I mean, basically this is the velocity in which the observer is traveling. So this derivative would be the same because it would be corrected or accounted for by this velocity.
And but I would be more interested in the velocity of the river. So don't you think the first term is going to be zero then? Because it's going to be time. Like if the second term is for the velocity of the boat, which can be anything, like so. But,
I don't fully understand your question.
like I was saying, like if the velocity of the boat is changing or whatever it is,
Mhm.
we're not interested in the velocity of the boat, but if we are interested in the velocity of the river body.
Yeah, yeah. So I think maybe my motorboat example is not really correct because the plume, the concentration,
Yes.
is traveling with the velocity of the river.
River, yes.
So I guess a more appropriate experiment would be two different rivers.
Yes.
You know, or one day you have one flow, and the next day you have a higher flow because they let water out of the dam,
Yes.
right?
Yes. Yes.
So in 2 different days you're gonna have 2 velocities of the river,
Yes.
right? Now, this value will be the same because it will be corrected for here. Yeah.
But if the velocity is same, like in one of, like you had one in the dam to release the water, but in the other one, if the velocity is same in the river, the river is flowing steadily. So I was thinking maybe the first term is gonna be zero then, because that's the local rate of change.
The local rate of change would be, again, it would be,
Can it be zero?
the local rate of change would be like essentially if you stop the boat, or and really what you should say is stop the river.
Yes.
If you stop the river but they were still pumping, if they were still pumping concentration into the river, then this would be the kind of what you're measuring there.
Okay.
Yeah.
And it doesn't depend on the boat, like how fast it's moving. Or
Yeah, again, yeah, boat really means velocity of the river, of the flow, right?
Okay.
Yeah. Yeah. Yeah, my motorboat example doesn't really work. It's like the flow, because you're measuring the concentration which is in the water. Right?
Yes.
Yeah.
Thank you.
Okay.